Okay, so today we're just going to do some review of section 1.0 and 2.0 in the electrical energy unit. Hopefully it's not going to be too long of a lesson today. You can obviously look at how long the video is right now and either roll your eyes at how I was wrong or go, yeah, he actually was right. It's not going to be too bad of a day. Anyway, here's the plan. So we're going to spend this class reviewing all the concepts from section 1.0 and 2.0 of electrical principles. So in other words, everything we've covered so far in this unit. The reason we're doing so is because we have a quiz that's going to assess all those concepts next class. It's going to be very much like the other ones we've done before, where it's a Google Forms quiz. I might start moving away from those. I think I'd like to see some written feedback from you. But for now, for this one at least, this might be the last one. We do like that, but for now it'll be the same old, same old. Anyway, I'll stop rambling. We're going to cover static electricity and current electricity today. We're going to talk about electrolysis and electroplating. We're going to talk about dry cells and wet cells. That seemed to cause some problems in the last formative quiz we had, so I really want to go over that again. We're going to talk about controlling the flow of electricity, so in other words, using resistors. We'll do a little bit about Ohm's Law. Hopefully that wasn't too bad, but there will be some questions on that quiz coming up. And then we'll look again at electrical circuit schematic diagrams, which, of course, hopefully you've done that assignment already. You should be a master at that by now. Anyway, let's get rolling. So, static versus current electricity. Hopefully you understand the difference. Static means not moving and current means flowing. So static electricity is electricity that's stored in one place. Current electricity is electricity that's flowing through something. So static electricity, again, where an object is holding on to a net electric charge, it could be either positive or negative. If you're wondering how to predict whether something has a positive or a negative charge, it's pretty complicated, and we don't really need to know how to determine that, of course, but you need some other sort of test charge, or you'd have to have some way of controlling where your electrons are going, if that makes sense. And remember, in order to have a charge, the only thing that moves are the electrons themselves. Those are the things that kind of buzz around the outside of an atom. Protons, which are the positive component, they don't move. They're inherent to an object, right? So in other words, you can't toss your protons to another thing. That'd be tossing the whole atom to something else. So a negative charge means it gained electrons, right? It has more electrons now than it did before. That means it's negatively charged. But if it lost its electrons, if it gave them up to something else, then it would have a positive charge. Because remember, the only charged thing left over now is the protons, which again cannot move. Current electricity is where your electrons are continuously being passed from one atom or ion to the next, and it goes at a very rapid pace. Next thing up, charge separation. This was really a struggle on that formative quiz we had. And again, maybe it was just because there was a good distractor question on there. When it comes to electrical attraction, opposites attract. I think we all understand that one. However, what is a little bit confusing is that neutral objects, things that don't have a net charge, can actually still be attracted to charged objects. And this is due to something called charge separation that happens within that neutral object. So the classic example, of course, is a charged balloon. Like maybe you took a balloon, you rubbed it on your head or something like that. So the balloon now has some sort of a charge. We'll say, because it doesn't really matter whether it's positive or negative, we'll just say it has a negative charge, as it is in this picture. It can be attracted to a neutral object like a wall, because a wall, of course, will have an equal number of positive and negative charges. And how it gets attracted to it is when you bring that negatively charged balloon close to the neutral wall, the positive charges in the wall are attracted to the negatives, and the negative charges in the wall are repelled from the negative balloon. So even though the wall still has just a neutral charge, it's got the same number of positives and negatives in it, it still behaves as if it was charged because those positive pieces within the wall are attracted to the negative balloon, and the negative charges are repelled from the balloon. This is also called polarization, right? Polarization is basically where you have one end become positive and one end become negative. So the outside of the wall in this case would be the positive, and the inside of the wall would be negative. Think of it like poles on the Earth, like the North Pole and the South Pole. It's two ends. There's a north and a south. It's kind of the same thing's happening here. It's becoming polarized, right? So one end and another. Next thing up, electrolysis. Electrolysis means breaking things down using electricity. That lysis part at the end, lysis means breaking things down. So electrolysis, breaking things down using electricity. So electrolysis can separate compounds into their components. We previously looked at an example where electrolysis can split water, which is H2O, into hydrogen gas, which is H2, and oxygen gas, which is O2, right? So it can kind of just do this chemical reaction and split that water apart. But what's actually really interesting for electrolysis, one of the things that it's most commonly used for, is you can actually like supercharge your object and remove the rust from it directly. So what happens is, kind of like with electroplating, you hook up the thing you want affected to a negative end of a battery, and your sacrificial piece, the thing you're going to sacrifice in this case, to a positive end. So if you had something that was rusty, and let's say it was a rusty pair of scissors, for instance, and the scissors are made of iron, you would need a positive charged piece of iron to use as a sacrifice here. And when you hook it up and you put it in some sort of electrolyte solution, usually they just mix water and baking soda, that works just fine, the rust gets electrically removed from the surface of this object, which is really quite fascinating. Now, of course, if you're ever going to try this, one, make sure you're using a safe enough battery and you're not going to electrocute yourself or anything here. And two, as you can see from this really disgusting looking picture, make sure you have a bucket you're willing to get rid of, because like this is a disgusting process. Like that bucket's going to be like destroyed. I don't know what they initially put in here. It's completely submerged. You can see these cables, of course, would be the negative end, leading down to whatever, like let's say with a pair of scissors they had down in the bucket here. And you can see on the positive end, and just so you know, positive, you should always use red cables on your positive end. It's just a good convention. We use red on the positive, but they have their red positive cable attached to just some scrap piece of iron. There was nothing wrong with it. It was just pure iron, and that's how they can remove the rust from this. Anyway, if you're interested in that, you can look up electrolysis to rust. There's a bunch of videos online. People use it all the time. It's good for restoring things that went rusty. Electroplating works in a very similar way. There was a question on that formative quiz a little while ago on electroplating, and it was really well done overall. Basically, it's just where you coat a metal object with a different metal using electricity. So how it works is the thing that you want plated gets hooked up to that negative electrode. There's a common theme here, right? You know, the thing that you want affected should always be hooked up to the negative end, and the metal you're using to plate with, so your sacrifice piece, is going to be hooked up to the positive electrode. So the solution as well, the electrolyte solution that you have these things dipped in, should ideally contain the ions of the metal you're using to plate with. So for instance, in this picture, they're using a nickel piece of metal on their positive end, because remember the long bar means positive and the short bar means negative on the battery. So the positive end, of course, is hooked up to your nickel. You're going to use nickel to plate this. It looks like a nail down there. Oh, it is a nail. It says right there. They're going to plate this nail with nickel. So ideally the solution, the electrolyte solution you have the stuff in, should also contain nickel. In this picture, they use nickel sulfate. The proper chemical name for that, of course, if you remember, throw back to our chemistry unit, because you got to watch your charges, it'd be nickel 2 sulfate. Formula for that is NiSO4. SO4 has a negative 2 charge. Nickel has a positive 2 charge. Because there's more than one possible charge in nickel, if you look at a formula sheet, or rather on a periodic table, you'd see that we have to say it's nickel 2. Anyway, that's a total throwback. I'm just rambling now. Anyway, bottom line is electroplating, really cool. You can use it to plate metal objects. Remember, the thing you want plated needs to be hooked up to the negative end, and the thing that you were using as a source of that metal should be the positive end. Okay, moving on. All right, dry cells and wet cells. I'm not going to spend a long time on this. The basic idea from this, and believe me, by the end of the week, we're going to talk about this in even greater detail, is that batteries, which are made up of cells, of course, basically convert chemical energy into electrical energy. So there's some sort of a chemical reaction occurring within a battery or within a cell to produce electricity. A dry cell uses this dry paste stuff, and once electrons start flowing through here, it causes like a chain reaction, and then the chemical reaction occurs and more electrons are emitted out that negative end of the battery. But also a wet cell battery, like you'd have in a car, it works under the same principle. It's just that the chemical reaction is occurring using a liquid electrolyte. So in other words, a liquid solution that's causing this chemical reaction to occur. Now, the pros and cons to this, of course, are dry cells can be used in any orientation, right? That's why we use dry cells in things like calculators or TV remotes. You can use it in any orientation. You can flip them upside down, really doesn't matter, right? It's not going to leak unless you punctured it or something, which would be a bad time. But wet cells, however, the reason we still use wet cells is they provide more bang for your buck. In other words, they're cheaper for what you're getting out of them. They provide more power for a lower price. Now, a car battery, of course, is going to be a lot more expensive than a single AA battery, for instance, but a car battery is going to produce way more power, way more power, and for a much longer period of time than, of course, just a normal AA battery. So that might have been what kind of threw a lot of people when we had this question on that formative quiz, because one of the things was, oh, wet cells are cheaper to produce. Well, they are cheaper to produce. If you were to produce an equally powerful battery, like if it was like a dry cell versus a wet cell, a dry cell would cost way more to produce at the same level of power as a wet cell would. Anyway, so that's why wet cells are only used in car batteries, because they're not as safe, and they're also cheaper, more bang for your buck, right? All right, resistors, we'll go real quick on this one too. We just covered this just last week. Remember, a resistor is used to control the flow of electricity. Changing resistance can affect either the voltage or the current. That comes out of Ohm's Law, which we're going to talk about in a second. That was V is equal to IR. So if you change your resistance, either your voltage or your current's going to go up and down. Now, increasing the resistance has an interesting effect on a lot of things. It often results in the electrical energy being released in different ways. So if you look at a stove element, the metal that's used to make that is different than the metal wiring that goes in and connects it, of course, to the wall throughout the whole stove. The reason that the stove element gets hot, but then the wire within the stove doesn't, is because the stove element itself has a different resistance. Pretty sure it's a much higher resistance than the wire that leads up to it. So once electricity is passed through the stove element, the increased resistance in here causes the energy to kind of go, hey, where do I go now? And it gets released, right? So the release of energy becomes thermal energy, so in other words, heat, and also, of course, a little bit of light energy because it glows. And that allows us to, of course, use our stove element and cook our food. Now, another thing that you need to know is a variable resistor. They're called rheostats. Some people just call them variable resistors, but rheostats is a shorter way of saying it. Basically, it allows us to control the flow of electricity. This is really useful in like light dimming switches, right? So you're controlling how much electricity is going through because there's a variable resistor in there. Also, volume knobs on old stereos. That controls how much like electricity actually gets through. In other words, it'll amplify the volume. Even on a stove element, like this just kind of came to me. Stove elements, of course, have different settings, like low to high and all that. That also would be a rheostat. You're controlling how much electricity is flowing through there. There you go. There's like another thing that would apply. All right, speaking of Ohm's Law, which I just mentioned, it's a mathematical relationship between voltage, current, and resistance. This pyramid is awesome. If you just remember, V is up on the top here and then IR is on the bottom. How it basically works is cover with your hand the thing that you want. So if you wanted voltage, just cover the voltage. I'll just scratch it out. And then you can see it's I and R, so I times R. If you wanted, let's say if you wanted the current, which is I, you just cover that and you go, it's V over R. Okay, so V divided by R, that's going to be your current. It's useful for me, at least. I've always liked using that. Here's a quick example. A current of 0.5 amps is flowing through a wire connected to a 12-volt power supply. Find the resistance. Okay, so we're looking for resistance. Cover resistance up. And then you see, it's voltage divided by your current. So 12 divided by your current. So 12 divided by 0.5. If you need a calculator for that, go for it. But 12 divided by 0.5, it's 24. And that's resistance. I chose this one on purpose. Do you remember what the units are in resistance? Hopefully, it's the weird letter. It's omega. So 24 omega, that's 24 ohms, right? 24 ohms, that's the resistance in that case. All right, moving on. Electrical circuit diagrams, we're almost done here now. You will need to be able to draw electrical circuit diagrams, at least at some point. These are also called schematics, okay? Not that you need to know that. Just remember that series circuits are where all the loads are in one direct chain. And the consequence of this is if one of the loads goes out, like a light bulb, for instance, goes out, then the rest of the thing in that chain goes out as well, because now your circuit is not complete. And of course, electricity doesn't flow unless it has a complete circuit. Now, parallel circuits are where loads are in their own chain, and they're all parallel to each other, right? So they're all like different lines of their own. The bottom line in this one is if one of those loads goes out, it doesn't affect the others, right? It just affects that one little line that it's in. All right, so these symbols, of course, are important to know. A lot of them you don't need to know, like, let's see, ammeter, you probably don't need to know that one. Voltmeter, you don't really know this one. Rheostat, you need to know what that is, but you're not going to ever put that in a diagram. But the other ones are fair game. Motor and fuse are pretty rare. We'll use them every now and then, like I think right in this next slide. Yes, we'll use a motor in this next slide. Here we go. So a circuit example, draw a complete electrical circuit schematic that contains a lamp and a motor connected to a 3-cell battery with a switch that can turn off both at the same time. Also, if either the lamp or the motor go out, it shouldn't affect the other. I would highly suggest right now pausing the video right here and trying to draw something. I'm going to draw one in just a second here, but I would love to see you guys actually give this a try. I think it'll really help your learning. Of course, I can't force you to do it, but please try pausing the video here and try drawing this on your own. All right, hopefully you did it. I'm going to go over this now. So again, since it told us that the lamp and the motor, if either one of them go out, it shouldn't affect the other. That tells us right off the bat we got to do a parallel circuit here. Also, another thing is our power supply is a 3-cell battery. These can be a little tricky to draw. I'm going to draw mine over here. Again, yours could look, there's so like infinite different ways you draw this, but I'm going to draw mine over here. So 3-cell battery means you got 3 cells in a row. So I'm going to do my negative end and then a positive. See, smaller one's negative, longer one's positive. That's just one cell though, so I'll do another cell, negative, positive, and then another one, negative, positive. So there's 3 cells there, 1, 2, 3 cells. And then of course I'll start connecting it to my wires. Now we want a switch that can turn off both at the same time. What's interesting about that is that means our switch should be placed outside of our parallel circuits so that it affects the whole thing. Safest place to put it is pretty darn close to the battery, right? So I'm going to put my switch right here. Now, just by convention, I like drawing my switches open. Some people draw them closed. I think it just makes it a little more confusing because then it's like, oh, there's little bumps or whatever. I draw mine open, so yes, it looks like it's an incomplete circuit, but whatever. I don't really care. I'm not going to be picky. If you want to draw yours closed, go for it. All right, so we have our battery. We're good. We have our switch. Now we need our lamp and our motor drawn in such a way that if one goes out, it shouldn't affect the other. Okay, here's how it's going to work. I'm going to draw my lamp in my first parallel here. A lamp, I usually just draw it by like making like a little break here with a circle, and then I do like a little whoop, 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 right? Doesn't have to be perfect. That right there, clear to me that that's going to be a lamp. Kind of looks like the filament in a light bulb. And then I'll complete that. Now this isn't done. I need to add another parallel to this for my motor. Now motors are a little trickier to draw. It's another circle, but then there's like the little dot right here, a dot in the middle, and then a dot in the end. And that right there kind of tells us that that's a motor, okay? So right now, if I just double check my work, I have my 3-cell battery right here. I have my switch right here. I have a lamp and I have a motor. And if one of these goes out, like if this lamp goes out, if that bulb breaks, we still have a complete circuit. Electricity can still flow through the motor just fine. And likewise, if the motor went out, like I don't know what would happen to it if it just broke, the lamp can still go because electricity can still find its way through. I'm drawing the electricity the wrong way. Electricity goes from negative to positive. So the electricity is going to flow this way. But anyway, still, one way or another, it works. Hopefully you drew that. It's really good practice. All right, so we're done. That wasn't too long of a lesson. A little longer than I thought it was going to be, 17 minutes-ish. That's not too bad. Now, for practice, any of the previous questions from week 7 or week 8 that you haven't yet completed, please get those done, of course. If you're not doing the practice questions, you are going to suffer a lot, of course, on these quizzes, right? So it's not going to be a good time. I'm going to be really watching these quiz results as well. I know some of you have already heard from me. If you're not doing very well in the quiz, I do reach out and go, hey, like, you didn't do too well. Do it over again, because you need to make sure that you're understanding this and not just screwing it up and then just saying, oh, well, I'm done, right? Keep in mind, I make these quizzes available so that you can do it as many times as you wish. So if you do it once and it marks it and it says, oh, you got a score that you're just not happy with, do it again, right? I think for anyone, a passing score at very least is what you should be aiming for at the like bare bones minimum. For a lot of you, I would say like getting 75 or 80% or higher would be ideal. You can complete it as many times as you wish. If I see that you bombed it the first time and then you retried it and you ace it, I'm cool with that. I won't be pestering you. So please make sure you're getting those done. Now the quiz must be complete by the end of Wednesday, May 27th. And also really, really important, if you haven't finished that electrical circuit assignment by now, please do. Hopefully everyone was able to access that app. Again, it's way better to do it on a computer than on a phone, but if you have to use a phone, then you have to use a phone. It's just a little bit more challenging to use it that way. Make sure you finish that assignment. Make sure you submit it, like the pictures, of course, that I asked in the assignment itself. And again, as always, if you need any help, please let me know.